And I'll go ahead and start recording down here as well. Hopefully it'll let me do it, and it did. Alrighty. All right, and hopefully we're still sharing. Are we still sharing? We're still sharing? Okay, good. Thank you. You know what? If we're face to face, it would be obvious if I was in the room or not. But we're not. All right. So anyway, we're starting chapter 13, which is properties of solutions. Oh, that sounds exciting, doesn't it? And it is. So we have what are called colligative properties. Okay, so let me make sure that I'm on the right page here. And let me get to it. Okay. Maybe we shouldn't start with colligative properties. Let's just start with just like, solutions in general. All right. So when things dissolve, so you have like a chlorine and a sodium, what happens? You end up with a ion of sodium and an ion of chlorine. That's what ends up happening when you have a solution. Okay. And so it takes energy. You have to have delta H to break apart. It doesn't matter what that number is. You just have some sort of energy it takes to pull these things apart. And then you have a delta H to form the ions in solution. And then finally, you actually, once you're forming these guys, well, guess what you also have to do? And this is a part that maybe is not completely obvious, is you actually have to push apart these solvent molecules, otherwise known as water. And I just want to emphasize this is three-dimensional. It is three-dimensional, although I'm a two-dimensional person drawing on a two-dimensional page. This is three-dimensional. And so you got all these water molecules around this thing. And this takes energy as well as to push apart. Because they originally started out, remember they have H bonding going on? Okay, so you actually had to slide in between. All right, they had H bonding going on. And so there's all these different energies going on. And as long as, the whole process is negative, which is delta H is exothermic, generally it's going to happen. It's going to dissolve. All right. Now, it doesn't have to be exothermic, it can be endothermic, but generally speaking, you want this to be energetically favorable when these things happen. Okay? And so when they dissolve, what do we got going on here? So here we go. So generally, we talk about solubility. And usually that's grams. And what are they using in this textbook? Is it grams per 100 milliliters or grams per 100 grams? Let's see. Let's go with grams per 100 grams of H2O. Depends on who you talk to, whether you're going to use grams per 100 milliliters, you're going to use grams per gram. Okay? Now, for something like, let's say that I'm trying to find an actual real world example here, because I don't want to just give you something that's not quite the same. So I got 170 grams. Let's say we have sodium acetate. And it's 170 grams per 100 milliliters H2O. Okay, at room temperature. Now, what this means, though, is that this is the most that can dissolve. All right, if you try to dissolve more than 170 grams, it's not going in there. All right, now what does that look like? And we have three different situations here. We have less and all clear, no solids. And then we have more than that number right there. And how can you tell? Solid on the bottom. All right, so if it's all clear, nothing's on the bottom. Okay, that means it's less than the solubility. If you have solids on the bottom, that means you have reached the solubility limit, which in this case is 170 grams per 100 milliliters, and any extra is going to go as a solid on the bottom. Any extras, okay? And so we give these special names, and we're going to call this unsaturated, which means it can hold more. All right, and when we see solid on the bottom, we're going to call this saturated, which means it can hold no more. That's what we're going to call it. We're going to call it unsaturated and saturated. Unsaturated, you can stir more in. So let's think about sweet tea. I love sweet tea as an example. I don't like sweet tea, but I like it as an example. Okay, so let's say you have unsweet tea. All right, and you have your little kid. I've got 4 kids, but many of you may not have kids. But here's my little girl. You've seen her many times, and here she is smiling. And she says, you know what? I don't like unsweet tea. And so what does she do? She takes open one package and dumps it in. You stir it up. Here it is, stirring away. All right. So what happens? It dissolves, right? You still have clear sweet tea. But my little girl, being my little girl, here she is again. This time she's in rainbow colors. And so she decides, you know what? There's this container of sugar on the table. You've probably seen this with the big glass, the big glass container, I don't know what to call it. It's big container of sugar, right? And so what does my dear darling little girl do? She dumps it in, right? And she just keeps dumping and dumping and dumping. Okay, so what happens? What happens? And I always ask you this: what happens? Well, what happens is no matter how much you stir, you have sugar on the bottom. Well, guess what? That's saturated. All right. So unsaturated is little girl with one package. Saturated is she's got the container and she just starts dumping. All right, that's saturated. You've seen saturated. Or you know what? When I was a kid, I don't know if y'all ever did this. When I was a kid, I would eat cereal. Nobody eats cereal anymore. But when I was a kid, I would eat cereal. And here I am. I was a very unhappy kid. And so here I am eating my cereal. Now, to make myself happier, to turn that smile upside down, what did I do? I would dump in a lot of sugar, okay, into my cereal. That would make me happier. But you know what? What did we have at the bottom of that cereal? We had what I would call sugar slush, or or as I prefer to call it, sugar milk, because it was milk with a lot of sugar in it. Okay, I don't know if anyone ever, sometimes I astonish myself at how many people have not experienced the same things that I have. Hey, there was this thing called sugar slush, and it was good. It wasn't good for me, but it was pretty good. And so, why did we get sugar slush at the bottom? It's because we exceeded the solubility. Now, it took until I was, 20 something years old, to realize this is what was going on. But that's what's going on. Okay. So if you see solid on the bottom, what does that mean? It means you're saturated. Okay. Now, typically, what we're going to do here is we got to figure out whether something's saturated or not. All right. Now, there is a situation where we exceed saturation. And you may say to yourself, how is that possible? Well, it can be done. And what it looks like is this. Let's say that the saturation was 170 grams per 100 milliliters, right? But what if you were able to get it to dissolve, let's say 250 grams per 100 milliliters, and you look at it and you go, all right, there's my eyeball pointing. Yeah, that's not a very good eyeball. But anyway, I'm pointing my eyeball there, and I see it's still clear. All right. What's happened here? Well, what's happened is you actually have exceeded the saturation. All right. There's no solid on the bottom. What also means is that energetically, it's not favorable anymore. Now, we call this supersaturation. In other words, we've gone above the saturation limit. Okay. And so not a whole lot of things will do this, but it does happen. It does happen. And if I was in class with you, I would show you a video, and you should look it up yourself, where here's a video. If you want to see this, it should be sodium acetate supersaturation. And if you pick the one that I usually show, it'll be high school students, and if you have PSD from high school, it will send you back to school. And so, yeah, it's a good video, sodium acetate supersaturation. So what happens is it's clear, and if you put a crystal, just one crystal, just crystal in there, all of a sudden it will all of a sudden start precipitating out and forming lots and lots of crystals. Okay. And it will continue dumping crystals until you get back to saturation. Saturation being what? You have the maximum to hold, and what's on the bottom? You have solid on the bottom. All right. So you go from supersaturation to saturation, and you have a bunch of crystals sitting on the bottom. Now, if you watch that video of sodium acetate supersaturation, it's a fun little video, and it'll take like 1 minute out of your life. If you watch that, you'll see that it ends up being almost entirely crystals. Well, that's just because sodium acetate you can dissolve a lot of it. Okay, but you'll see. Okay, so it's a worthwhile video to watch as far as the saturation goes. Now, so as far as we go, as far as solubility goes, it is temperature dependent. It's temperature and pressure dependent. Solubility is. And okay, once again, we're into the whole hand waving thing. Okay, so I'm going to wave my hands around a little bit, but it's important that you be able to follow the trends. Okay, so the first thing is solids in water. Which way does it go? As I increase temperature, what happens to the solubility per 100 milliliters? Now, what I want you to think about is sweet tea. Sweet tea. And has everybody ever made sweet tea? I'm sure you've made sweet tea, or at least you've seen someone make sweet tea. And how do you make sweet tea? You take a little bit of water with a whole lot of sugar, right? At least down in the South, this is how you do these things. But what do you have to do to get that sugar to dissolve? You have to heat it up. You put the sweet tea, you put the tea on the stove, you heat it up, then you stir in the sugar. What are we really saying? What are we really saying? And so what we're really saying is as you heat up the water, what happens to the solubility? It goes up. So sucrose, otherwise known as sugar, as you crank up the temperature on your sweet tea, guess what happens? You can stir it in more. Why can you stir it in? Because you're increasing the solubility as the temperature goes up. The solubility is different for different things. And so sodium chloride, for instance, which interestingly enough, doesn't change much at all as temperature goes up. That has some real implications. You figure out, the poles are cold, the equator's hot, solubility changed a lot. Just think about it. Well, what happened, right? You get these mounds of sodium chloride depositing out on the poles, and then the equators would not have any salt at all. And then you have an occasional compound which goes down ever so slightly. I think cerium's one of them. Cerium sulfate, I believe, is one of them. It actually goes down a little bit. And this is important for things like if you ever work in a factory and you have a boiler, they have these salesmen that run around giving you water treatment chemicals. And the sole purpose of water treatment chemicals is to keep from messing up your boiler. Because if they can start precipitating out at high temperatures, because that's what boilers do, well, guess what happens? You get all this crud that's on the inside of the boiler. Okay, so you have to be careful about this stuff. It's like, oh no, you don't want this sort of stuff precipitating out on the inside of your boiler. So you pay a lot of money to get rid of it. But then you have some other chemicals like sodium nitrate that probably go about like that. Okay, so it all depends on temperature. It's very temperature dependent. But what can we say from this? What can we say? Because remember what it's all about. It's like, what can you really say? What are we really looking at here? Solubility goes up with temperature. Generally. Okay, not always. But what can we say? Solubility of solids in water. You heat the water up, guess what happens with sweet tea? It goes up. Okay, it goes up. And you can stir some more sugar in there, yeah? So solubility goes up with temperature, but I do want to point out, we're sciencey sort of people. supposed to be sciencey sort of people, not always. Okay, not always, most of the time. Most of the time. Okay, so sugar, yeah, there's sucrose. What's it doing? You crank up the temperature, solubility goes up. So there you go. All right, sodium nitrate, fertilizer. What happens? Hotter the water gets, the more dissolves. These cerium compounds, not so much. Not so much. Is it important to know? Not really, as far as specifics go. But in generalities, it's important to know that solubility goes up with temperature for most things. Most things. Okay. Now, we have another situation going on here. Well, you know what? What else dissolves in water? How about gases? And you may say to yourself, what do you mean gases? I mean, what are we talking about gases? Well, do you have fish? You ever heard of fish? What do fish breathe? Fish do not breathe water. Fish are breathing the oxygen that is in the water. Yeah, so that's an important distinction. Fish don't breathe water; they breathe oxygen, just like me and you. Well, at least I'm not so sure about myself, but I'm pretty sure that you, as being human beings, breathe oxygen. Me, on the other hand, I'm not so sure. But look, fish breathe oxygen. Now we have so many grams per 100 milliliters again, and degrees Celsius. Now, it goes the exact opposite direction. Solubility of gases actually, without exception that I know of, goes in the opposite direction. As the water gets warmer, gases go down with temperature. Now, why is this important? You ever heard of fish kills? This is what you're going to think about. Remember when I said about solubility of solids with temperature? Sweet tea, right? You're going to remember this because you're going to remember fish kills. Now, oddly enough, when I ask people when I'm doing face-to-face classes, I ask them, I say, have you ever heard of fish kills? And a lot of the class just kind of looks at me and goes, what is this that you speak of? And I'm like, surely you've heard of this, right? Fish kills, you open up the newspaper back when there actually were newspapers. You open up the newspaper and you say, wow, a lot of fish died, right? And then, the politicians start blaming the pig farmers, and they said the pig farmers are responsible for the fish dying and all that. But it all comes down to oxygen in the water, because guess what? Fish need to breathe, and that is oxygen. And so when you see fish kills, hot days, ooh, like now, right? It was like 100 degrees outside yesterday. Well, guess what? Fish don't like that, because guess what happens to their little, ooh, I got blue. Guess what happens when the fish are swimming around and it all of a sudden, well, there's a blue fish, but it's a very unhappy fish. You know why he's unhappy? Because it's 100 degrees outside. Well, not 100 degrees Celsius. Yeah, what is that in Fahrenheit? I don't know. But, it's like 100 degrees Fahrenheit outside. And what happens to the fish? Well, they've gone from happy fish to very dead fish. That's what happens. Okay, so that's the point of this whole chart here, is to show you that as you increase temperature, solubility gases decreases with temperature. And how we're going to remember this is we're going to remember that unhappy fish. Okay, we're going to remember the unhappy fish because that's what's going on right there. Okay. All right. Let's see what else we got here. Expression concentration, and we have colligative properties. Tell you what though, I'm gonna save colligative properties for Friday. Okay, because it's a whole lot of calculations. Okay, everything we've done so far has been kind of hand waving, general descriptive. As temperature goes up, solubility goes up for solids. As temperature goes up, solubility goes down. There's forces pulling these things apart. There's forces involved in here. So what I'm going to do is Friday, we're going to do colligative properties. Now, what are colligative properties? Colligative properties are based on how much you have. Colligative means the collection of the whole thing. And so we're going to do colligative properties on Friday. And so let me give you a preview. That means on the collection. And it affects things like freezing point, boiling point, and well, what else do we have here? We have vapor pressure, and we have something called viscosity. All right. All these things are going to be affected by colligative properties. So we're going to do that on Friday, okay? That's what we're going to do. And so freezing point, boiling point, vapor pressure, viscosity, we have boiling point elevation, we have freezing point depression, all these things, okay? So that's what we're going to do on Friday, all right? Okay. And then we're done. We'll be done. And then it's up to you, all right? So there you go. So any questions before we call it a day?
Did you have a class yesterday?
I did. I haven't posted the video yet. Unfortunately, because of the COVID-19 thing that's going on, the processing time on these videos takes forever because everybody's processing, but I will go ahead and post that. But what we did cover yesterday was we did a couple of calculations for that we did the lab on. In other words, how much energy does it take to melt the ice? How much energy does it take to warm the ice? How much energy does it take to vaporize? That sort of thing. And that was pretty much it. That's what we did yesterday. Okay. I'm pretty sure the video is finished processing, and I'll go ahead and get it posted pretty quick.
Okay, thanks.
Yeah, if you have this unrelented urge to watch chemistry. But anyway, yeah, I'll go ahead and get it posted. But yeah, I did do yesterday. I was trying to make up time because I missed last Friday. I was stuck at the doctor. Did y'all get my email? I was, imagine that. Yeah, got stuck at the doctor. And she says I'm in great health. So there you go. There was some positive aspects to the whole thing. But anyway, I'll get the video posted shortly. Okay. Promise you, I will. Or at least the link. Other questions? All right then. So, hey, look. Oh, before you go, if you have any assignments that you need to make up, quizzes, homeworks, whatever, email me, please. Okay. We got less than a week to go, right? Something like that. Less than a week. Don't want to, if you have anything you need to make up, just let me know. All right. Just saying. All right. Having said that, I will see y'all Friday then.